Thank you very much, Francisco, for the invitation to come and talk to you today. I very much enjoyed the last time that I was here 2 years ago. It's been on my mind to come back and talk to you again. But obviously I needed something new to talk about, and we do have something new. Perhaps you've been reading the press recently. You will have seen that there is some new discoveries that we have to talk about. And so this will be the subject of my talk today. But I also thought I'd try and give a little bit more of a kind of wider view of this. Often when people mention dark energy, it's somehow in passing, because really what people like to talk about is something that they can build a whole hour's lecture around. People like to talk about stars, they like to talk about galaxies, because these are very concrete things that we can observe, and we can say concrete things about it. So often people will flash up some graphics and say, okay, 2/3 of the universe is dark energy, and then they'll very quickly move on to talking about something that they're much more comfortable talking about. So we'll confront this head on today. We'll actually try and answer some questions about dark energy, frequently asked questions, if you will. And I can't promise complete enlightenment, but hopefully a little bit more enlightenment than when we started. Okay, so let's begin. And where do we begin? Well, of course, you know the chap on the left very well from his picture. You might not know the chap on the right very well. His name is Arthur Eddington. He was a famous astronomer in the early part of the 20th century, and he helped establish Einstein's theory of general relativity as the correct theory of gravity, because he travelled halfway around the world to observe the bending of light from distant stars by the gravity of the sun during a solar eclipse. And he was very interested in dark energy, and I put this quote up from him. It's actually not to do with dark energy, but it's still a great quote. Something unknown is doing we don't know what. Okay, so that was the view in 1930s, I guess, this is probably when this picture was taken. Let's see 100 years later what we have learned. Okay, so just a bit of background. We have a snapshot of a very early universe, which is the cosmic microwave background. That is the oldest light in the universe. That came from us from when the universe was about as hot as the surface of the sun, and it cooled, and that light is still flowing through the universe today. And when we look at the pattern of that light, it doesn't tell us very much about dark energy. Dark energy is in principle there, but it's a very, very thin slice, and so thin that we can't actually see it. Now, if we go to the universe today, what we think we see, and I'll come on to why we think this, is we think that dark energy makes up 2/3 of the energy budget of the universe. Dark matter is 25%. Now, we don't know what dark matter is either. What we do know, the atoms that we're made out of represent only 5% of the energy budget of the universe. All of the stars, all the galaxies, you, me, atoms, just 5%. So, how did we get to this picture of the universe? This might surprise you. This is a picture of Isaac Newton up here, and I'll explain the connection between him and dark energy now. This is an excerpt from Principia Mathematica, Newton's famous book. Now, Newton didn't write a lot of equations in his book. He argued from the terms of geometry, very much like inspired by the ancient Greeks who regarded physics as really just a branch of mathematics. So Newton, being a good geometer, likes to argue from symmetry principles. And one of the things that he wanted was that if you consider the gravitational force of the Earth, here I am stood on the surface of the Earth and gravity is pulling me down to the middle. Now you might know that the force of gravity according to Newton is Gm divided by r squared. But what m and what r squared? A bit of the Earth is very close to me here and a bit is far away in Australia. What Newton wanted was that he wanted the m to be the whole mass of the Earth, and he wanted r to be the distance from me to the centre of the Earth. So if I took all of the mass of the Earth and I concentrated it into a small block right at the centre of the Earth, me here, I wouldn't feel any difference. So Newton wanted that as a principle of gravity. But the mysterious thing that he discovered when he worked through the calculation was that there are two force laws of gravity that satisfy that symmetry principle. And you can see here, the words that he put attract each other mutually, as is the distance between the centre of the spheres. In other words, the force does not decrease with distance. The force in this alternative, perfectly consistent view of gravity, mathematically consistent that is, increases with distance. Now, if you've done A-level physics, you might recognise this as Hooke's law. This is the force that will be exerted by a spring, where x is the displacement of the spring away from equilibrium. So if the force increases with distance, the force between me and the first row is half the force between me and the second row. So you can start to see, if I have a force increasing with distance, things that are further away will look as if they're accelerating away from me. So Newton discusses this, and he says, okay, two force laws in this part of the Principia. One is the standard inverse square law, and one is funny law, which force increases with distance. And Newton expresses surprise, which is very remarkable. And that's the only place I am told in the entire Principia where Newton allows himself an expression of emotion. So Newton is surprised by this. Now, of course, Newton knows that this force doesn't agree with the motion of the planets in the solar system, so that's where he drops the idea. But I still think it's interesting that in some sense, the idea of dark energy originated with Isaac Newton. Okay, now let's go through in time to Einstein. 1915. Okay, so 1915 is when Einstein writes this equation. This is Einstein's field equation. This is the law of general relativity. Remarkable. And it's such a beautiful equation. It's so simple the way it looks. Now, I'm not going to go into the details here, and it doesn't really matter for our talk, but it's a beautiful equation. On the left-hand side, we have space. So that's what big G represents. And on the right-hand side, we have big T, which represents matter. So in the words of John Wheeler, who's an astrophysicist in the US who spent a lot of time doing calculations in general relativity, the encapsulation words of this equation is matter tells space-time how to curve, and space-time tells matter how to move. Now, Einstein wrote this in 1915. What he did in a paper in 1917, 2 years later, was to add this term here. Now, lambda is a constant. And it doesn't really matter the difference between big G and little g here. They're both basically space. Now, it turns out that this is the only term that we can add to Einstein's gravity that still satisfies properties that we like, such as continuity of energy. I think of a box, the flow of energy into the box has to equal the change of energy in the box. That's quite a nice property for energy to have. And that only works if lambda is a constant in nature, like gravitational force constant, or maybe the charge of the electron. So why did Einstein do that? Why did he take his original beautiful equation and tack on what looks like a fairly ad hoc term? Einstein's reasoning is quite subtle, as it usually is. Einstein argued in the following way. He said, well, the distribution of stars in the universe is finite, or it is infinite. What he means by finite is that the Milky Way is an isolated universe of stars in an infinite void. Now, remember, at the time that Einstein was writing this was not known. It was not known whether there were other galaxies in the universe. This was a famous debate that happened between Shapley and Curtis at the time after Einstein wrote this paper. Now, what Einstein points out, if it is finite, if we have just this isolated island of stars, from the gravitational interactions of the stars, occasionally a star will be ejected from the galaxy at escape velocity. It will leave into the infinite void, never to return. In other words, the galaxy evaporates. Now, this obviously is inconsistent with the existence of galaxies. So Einstein then says, well, okay, if the distribution of stars is infinite, in an infinite void is evenly populated with stars, there is another problem. Gravitational potentials are infinite in that universe. And here's the reason why. If you imagine a spherical shell of stars surrounding us with some thin thickness, the mass of that spherical shell is proportional to its area times its thickness. Okay, let's leave the thickness out, but that means that its area will be proportional to the square of the distance it is from the area of the sphere. Now we know from Newton's law, and then Einstein's equations replicate Newton's laws at low masses and low energies, that the potential energy is proportional to the inverse of the distance. So I have a mass that increases with the square of a distance, potential that only falls off as 1 upon r. So when I put all that together, the further out I go, the bigger the potential energy it generates, and eventually it's infinite, which can't be physical. So this is a dilemma. Both seem to be giving us the wrong answer. So Einstein's answer to this dilemma was to add this term into his equation. He called it the cosmological constant. And what it does is it cancels the force of gravity. It adds in a negative term to the potential, which cancels the matter. And if that value is just right, you can imagine, obviously it has to be related to the density of stars, then, as a byproduct, the universe is static and eternal. And Einstein doesn't mention it explicitly, but he seems to have liked this idea. I guess this is a little bit philosophical, but maybe some scientists at the time, were not particularly religious and didn't like the idea that the universe might have a beginning because it smacked of God. So to have a universe that is infinitely old, static, and eternal, I guess might seem aesthetically pleasing. So maybe that was also part of Einstein's motivation. The trouble is, you can imagine, just like as if I have a stone hovering in the air, where the force of gravity is trying to drag it back to Earth, but I've added in this anti-gravity term that is now making it hover. You can imagine what happens if there's just a little bit more anti-gravity. The stone would shoot up into space. If there's too little, it would fall back to Earth. So this is unstable. Einstein didn't realise that when he wrote this down. But of course, it was quickly pointed out. And of course, following the discovery of the expansion of the universe by Edwin Hubble in 1927, Einstein abandoned his idea of a cosmological constant, reputedly calling it his biggest blunder. And so the matter rested until 1998. Now, in 1998, Saul Perlmutter, there he is, was leader of a team looking at something called supernovae. Now, supernovae are exploding stars, and they come in different flavours. The flavour that he was particularly interested in is called Type 1a, and it's believed to originate in the following way. You have a binary star system. One is just a regular star. The other is a white dwarf, and the white dwarf is the collapsed core, as you know, of an old star that's now finished its fusion. It's just the dead core that's left. Now, for the right orbit, that dead star could accrete material from its companion. And when that material reaches a critical mass, just like a nuclear bomb, it explodes. In other words, it's a star-sized nuclear bomb. And there's a picture of one in a nearby galaxy, and it goes off with a brightness roughly equal to the galaxy. It's an enormously bright event. That's one star with a brightness of about 1 billion suns. So as a result, we could see them halfway across the universe. Now, if it's a standard bomb, we know the energy input, right? And therefore we know the brightness, the intrinsic brightness of that. They're all the same, right? Because they all explode when they reach critical mass. So all we have to do to work out how far away that supernova is just look and see how bright it is. Just like a line of street lamps receding into the distance, the ones further away, again by the inverse square law, will be dimmer than the ones closer. And we can convert the brightness that we see immediately into a distance, very accurately. So when we see a supernova exploding a gigaparsec away, from its brightness we can immediately tell how far away the galaxy that it exploded in is. And we can build up, by observing many of these supernovas, we can build up a roadmap of distances in the universe. And from the differences in those distances of neighbouring explosions, we can work out the expansion history of the universe. And when Saul Perlmutter did that, it didn't agree with the model at the time. The distant supernovae were too dim. I'll come into what that means in a minute. And as a result, when he did the calculation, it showed that the universe was accelerating. And let's actually look at the data that he had. Can you see a straight line here? That was what people believed. When I did my first cosmology course back in 1991, this is what I was taught the universe was made out of matter. Omega M equals 1 means 100% matter. And lambda here is your dark energy, 0% dark energy. So that's the prediction you would have for the data if the universe was made 100% out of matter. But you can see here that blue dots do not line up to that model. And they line up to a different model, which is only 29% matter and 71% dark energy. So that's the data that gave us the feeling that the universe was expanding. So from the dustbin of history, 70 years ago, the concept of dark energy was suddenly right front and centre. And of course, people hadn't entirely forgotten what Einstein said. So, lambda was the most obvious explanation for this data at the time. Now, there was another team by Adam Rees, and this is great. So you may know they got the Nobel Prize for this discovery, and Adam Rees, in his Nobel Prize lecture, published emails that he received about all of this from his team. So here's a question like, you think you've discovered something that really changes our understanding of the universe. What does your team think about this? You can probably see they weren't entirely enthusiastic. Wrong, silly, very perplexing gaffes. And that's your own team. Imagine what the opposition are going to say. Fortunately, there was one guy who said something sensible. If you're really sure that the cosmological concept is not zero, my God, get it out. Take your responsibility as organizer and grunt. You will probably never have another scientific result that is more exciting to come your way in your lifetime. It's true. 30 years have gone past, and until recently, we did not have anything as interesting as this to say about dark energy. In fact, probably Adam Rees need not have worried, because I think to some extent now in retrospect, it's easy to say, of course, in retrospect, but the clues were already there. The very first galaxy surveys had suggested that the universe was not 100% matter. It was too underdense. So in fact, actually, the community took to this fairly quickly without a great deal of opposition. Okay, so let's get through to the present day. And good, because it's roughly the halfway point of my talk now. So to summarise, in 1998, we had the first indication, good indication, very strong evidence that there was such a thing as dark energy. Now, see, I put up here a logo from an experiment, a telescope called the Dark Energy Spectroscopy Instrument. It's on Mayo Peak in Arizona, in the US. UCL is very involved in this. We have a number of people working in this collaboration. And in March 2024, and also again in March this year, and it was really the one this year that made the headlines, they published new data. Rees and Perlmutter had enough data to say that dark energy was there, but not to say anything else about it. New data is showing that it may not be possible. I'll come on to that in a minute, what that new data is, but you can see it got reported on the BBC, it's part of Gauche in France. It achieved the remarkable thing of knocking Donald Trump off the headlines of newspapers around the world. Russia, China, Turkey, etc. It was. Yeah, I've never had a talk that's grim and clear, you see. Okay, back to business. So what was it that Desi did that changed our minds about dark energy? What Desi is looking for, and this is an image I got from ChatGPT, they're looking for spherical ripples in the pattern of galaxies. Now, I don't really need to explain where these ripples come from. They originate from a very, very early universe, and there are seeds of overdensities in the early universe. And when the universe was hot, it was a plasma, and they propagated like sound waves. And because the universe became transparent at a particular time, those sound waves traveled a particular distance. And in today's universe, that distance is 130 megaparsecs, or about 130 times the distance between us and Andromeda. And we can see these ripples. We can see them in the patterns of galaxies in the sky. And it's like a standard ruler. So just like the supernovae were standard candles, these are standard rulers. If we measure the angular size as they appear to us, we know the absolute size, we can work out the distance. So this is a graph that I made of the data. Now, the blue dots here are supernovae that we actually collected 1,800. This is a collaboration I've been involved in deeply. So for 6 years we collected supernova data. That telescope is in Chile. We put that data together with DESI's data from their telescope in Arizona. The blue dots are our data, the supernovae. The green dots are DESI's data, and they're a little bit bow ties here. And the game that we're playing here is which model fits the data better. Here I've put Einstein's cosmological constant, and here I've put dark energy is changing. And the game that we play is the model that fits the data better is the one where the dots are closest to the horizontal line, and the little bow ties are closer to horizontal. So this is actual data. This is what we have. This is the evidence. And you can see that the evolving dark energy just seems to fit the data. You can see that visually by eye. It seems to fit the data better than the Einstein's cosmological constant. That raises the question, well, if it's changing, what is dark energy? If it's space, how does space change? It's unclear. But if it's matter, what is it? What makes it generate this weird acceleration property? Maybe it's a new force in nature. So it raises this question, okay, it's no longer constant, but it doesn't tell us yet what it is. So let's have a think. And let's now zoom out from our gift box of dark energy, here it is, to the universe. Now, what I've explained to you is distances to exploding stars give us a clue that there's a thing called dark energy and it may be changing. That seems very intangible. What about actually thinking, can we measure dark energy in a box? If this box contains dark energy, is there some way that I can measure it directly in the laboratory? So here's Einstein's equations again with his cosmological constant. Now what I've done here from these two slides is that I've moved the cosmological constant from the left-hand side of the equation, to the right-hand side. And I've called it a T instead of a G. But it's the same thing, right? This is just a mathematical rearrangement. Now I could say, what if dark energy was like matter, what kind of matter would it be? And the weird thing is, for it to work like the cosmological constant did on the left-hand side, it has to have negative pressure. Now let's think about a balloon of gas, okay? So the little molecules of gas bouncing around inside the balloon, they exert a force which pushes the balloon outwards, positive pressure, okay? Dark energy, for it to be dark energy, has to have negative pressure. That's very weird. We know of no form of matter that has negative pressure. Regular matter, just like dust spread around floating in the universe, has more or less zero pressure. Light, I've used slightly funny units here, non-physical units, but it's a little bit normalized. Light has about pressure equal to 1/3 of its energy density. This is what we understand as normal stuff. So this is profoundly weird to have negative pressure. Now, why does that matter for gravity? Pressure comes from the kinetic energy of all of the molecules bouncing around. Now we know E equals to mc squared, right? So if I have kinetic energy, I have an energy. And energy is equivalent to mass in Einstein's theory of relativity. Mass generates gravity. So if I have negative pressure, I have something like a negative kinetic energy, and therefore a negative term of gravity. So that my P equals to minus rho there, that's what makes the anti-gravity. So dark energy is like anti-gravity because it generates a negative source term in the equation. So that's thing one about dark energy, it's anti-gravity. Thing two is that it's spread evenly everywhere. Now, the sort of details of this are a little bit technical, but let me make an analogy. Dark energy is a bit like the antisocial person at a party. Imagine a whole party full of very antisocial people. They like to avoid each other. That comes from a negative pressure term. So dark energy, because of its negative pressure, has to spread out and organize itself evenly around the universe. In contrast to normal matter, which you know likes to stick together. Now imagine that we have the sun and the earth, okay? Now in between the sun and the earth, there's a quantity of dark energy. I've represented it here as like a sphere, like a ball of dark energy surrounding the sun. Now that ball will have mass proportional to the amount of dark energy, the cosmological constant lambda, times the volume, okay, r cubed. But we know the gravitational potential decreases 1 upon r. So I can modify Newton's law of gravity and add on this extra term right at the end. And you might remember from Newton, that thing I put at the beginning, and remembering that force is the gradient of the potential. This is exactly the term that Newton wrote down in Principia. If I differentiate this with respect to r, I get a force proportional to the distance. So this is exactly, again, Hooke's law. Now you might think, what's special about the sun? Why did I locate this on the sun? It doesn't matter. That's just a mathematical convention. I could have located it anywhere and said, okay, it's the centre of the Milky Way or something like that. If you think about it, it will generate acceleration of everything away from each other, irrespective of what I regard the centre to be. So, to move on to our next frequently asked question, how much dark energy is there? Well, I kind of said on the box that there's 10 to the minus 29 of a gram in this box. That's the calculation. And it's more or less twice the amount of matter. You might think, oh, that's really low density. You know, why is there so little matter in the universe? Well, think about it. So that the galaxy is a concentrated chunk of matter, but there's an awful lot of space between us and Andromeda. If I take the mass of the galaxy and I spread it out evenly everywhere between us and Andromeda, I will also have about the same density. So that's why there's so little dark energy in this box, is because it's spread out. Even though there's twice as much of it as matter, it's so evenly spread out. It's about equivalent to 4 hydrogen atoms per cubic meter. So you can imagine trying to detect the force of 4 hydrogen atoms in a box at a meter cubed in the laboratory is quite unrealistic, unfortunately. In fact, if I took all of the dark energy in the solar system between us and the orbit of Pluto, and I somehow had a machine that concentrated it into a lump, the amount of that dark energy would be about the mass of a small asteroid. So this is why we can't detect the effect of dark energy on the orbits of planets in the solar system. The mass of the sun just dwarfs the mass of dark energy in the radius of our solar system, and we can't detect the effect of dark energy on the orbits of planets despite its anti-gravity effect. Nevertheless, it's quite interesting how NASA works sometimes. NASA has this blue sky proposal scheme. Anybody can write in a proposal mission. This mission proposal is called GODDESS, short for Gravity Observer for Direct Detection of Dark Energy in the Solar System. It's very much a blue sky proposal, but it's been through at least one round of review and has survived it, so who knows, it may fly someday. And it's a proposal to measure dark energy through its relative acceleration of 4 satellites flying in a constellation with incredible sensitivity using a quantum mechanical technique called atom interferometry, which is a bit similar to LIGO, how gravitational waves are observed, but different. It needs to reach a similar sensitivity to a space-bound gravitational mission which is going to launch in the mid-2030s called LISA. So there is perhaps a little prospect that one day NASA will approve this mission and we will have a detection of dark energy in the solar system. And if you want to know more about that, I'll put a link at the bottom there so you can follow it up. It's on the NASA website. Very cool. Okay, what about the Milky Way? So it's a solar system, tricky. What about the Milky Way? Now, our Milky Way, if you think about the volume, it has 10 million solar masses of dark energy. It's a lot, but the Milky Way has 60 billion solar masses of dark energy. So again, expecting to detect this from the orbits of stars in our galaxy is unrealistic. However, I think now expanding our view to the volume between us and Andromeda and calculate the amount of dark energy there must be there, and that's now 30 billion solar masses of dark energy. That's now starting to get galaxy size, right? So maybe there's a chance. Now there's a very interesting argument here which exploits that idea, and it's called the timing argument. Now, bear with me a little bit, it's a convoluted argument, but at the Big Bang, the density seeds that later went on to form the Milky Way and Andromeda were there, right? They were just density seeds at that point, but they were on top of each other because that's how the Big Bang works. Everything is on top of each other at the Big Bang. So they flew apart from the initial velocity of the Big Bang. But today, Andromeda is travelling back towards us. And we know that because we measured its velocity and it's heading towards us. And it's heading towards us. We know roughly the distance to Andromeda, we know its velocity. So Andromeda will collide with the Milky Way in about 3 billion years' time. But they initially flew apart, they reached an apogee of the orbit, and now it's on its way back to the Milky Way. So that's a regular orbit which we can run through a calculation. If we know the masses of the object, we know the time, we know the initial conditions, we can calculate the whole orbit. So the key here is knowing the masses of the object, knowing the mass of the Milky Way and Andromeda. So I can make a calculation and compare that to what I see. And this is the result. Lucy Partridge was a PhD student here at UCL, Offa Lahav, that runs the cosmology group here, so this is a UCL paper. Now, we know over time that has elapsed since the Milky Way and Andromeda were on top of each other. We know the initial conditions because that was a Big Bang. So we know we're on this red line here, that's today, 13.8 billion years after the Big Bang. And this is what the orbits tell us. Now, if we knew the mass of the Milky Way and Andromeda, we could go from that y-axis here across until we hit the red line, and we could say, okay, where do we hit the red line? If the mass is 6.2, I hit the red line about here, and that means that that's consistent with a cosmological constant. If, on the other hand, the mass of the Milky Way and Andromeda are just below 5.5, that's a little bit of a problem for dark energy. So very, very clever arguments. So in other words, it does have a material effect on something that we can observe in our local universe. Unfortunately, we don't know masses of the Milky Way and Andromeda that accurately yet, but there's a good chance that we will in the near future. So kind of watch this space. That's a theoretical calculation. We're very much interested in knowing the masses, and hopefully we'll know that relatively soon. Okay, back to DESI. Right, so DESI suggested that dark energy is weakening. So what does that really mean? We need some new parameters to describe how it's weakening. And the key parameter here is WA, which describes how the rate of change of dark energy with the expansion of the universe. And W0 is its strength today. Einstein's cosmological constant is up here, so it doesn't change. So WA is 0. And this W parameter relates pressure and density. So remember I said that pressure was equal to minus the density, so W is -1 in Einstein's cosmological constant. That's the proportionality of pressure to density. So dark energy is weaker today than Einstein's cosmological constant. Remember, matter is 0, so it's somewhere in between the constant and regular matter. And it appears to be changing. It has a non-zero WA. Now, the strength of it, and these are kind of like probability contours. The strength of a detection we normally quote as a sigma. And a sigma translates into odds that we could be tricked by the data, right? We only have one universe to observe. The data might have just wobbled in a particular way and made us think that dark energy was evolving, but in actuality it really wasn't. And we express that as an odds. Now, the gold standard for a discovery is 5 sigma, which is odds of 3 million to 1 that the data is tricking us. So the significance quoted by Desi is 4.2 sigma, which is almost there, but not quite. It's still, odds of I think it's about odds of 700,000 to 1, or maybe tens of thousands to 1. But yeah, not quite gold standard yet. And of course, if you see what similar age to be, perhaps you remember Carl Sagan's program in the 1970s, right? Cosmos. He wasn't just on TV, he was a proper scientist, and he had a very well-known quote, great quote: extraordinary claims require extraordinary evidence, right? So it's the extraordinary claim that Einstein was wrong. So we should require extraordinary evidence to prove that. Now, the weird thing about the graph that I had on the previous page is that when you kind of run through the implications of that, if dark energy is weakening today, it must have been stronger in the past. Now, it gets so strong in the past, it becomes this weird thing which we call phantom dark energy, which violates certain energy conditions in general relativity. Now, it's not impossible to violate that, but weird things happen if you do violate them. Very weird things, which we generally believe to be unphysical. So in other words, the data that I showed you on the graph suggests that dark energy is doing something profoundly unphysical. Not just acceleration, but profoundly unphysical. So many scientists are skeptical. In fact, from my estimation, roughly half people believe Desi's results and half don't. So there is still some, despite the strength of the evidence, there is still some doubt in the community. Now, let's move on. This is one of the big questions. What is the ultimate fate of the universe? If we were here in the universe 20 billion years from today, what would we see? And the fate of the universe is tied up with dark energy. Now, in Einstein's universe, what happens is that the expansion rate of the universe decreases, but it eventually plateaus, and it reaches a constant rate. What that means, obviously, stuff that's further away is still moving away from us. As it moves away from us, its speed appears to increase and accelerating. Stuff continues to accelerate away from us. And eventually, that stuff is accelerating so fast that the light emitted by a distant galaxy would never reach the Earth. That galaxy would effectively disappear from view. So if you imagine us standing on the Earth 20 billion years from now, what we would see is the distant galaxies recount, one by one. Their light would disappear. Eventually, closer galaxies would disappear too. And we would be left alone in the void. The local group would still survive because it's a bound gravitational system that's decoupled from the expansion of the universe. So we would still have Andromeda, but that would be it. We would be alone in the universe. That's Einstein's universe. Now, a very weird thing happens. Remember this W number here. So Einstein's constant W is -1. In principle, W is a variable number. If W is less than -1, very unpleasant things happen in the far future. It's called the Big Rip. Dark energy, as space expands, makes more dark energy, and this happens at an ever-increasing exponential rate, until eventually so much dark energy is being made so fast, the universe ends in something called a Big Rip. So what does a Big Rip mean? Well, it means that the universe is now expanding infinitely fast. And it happens in a finite time. This is really surprising. If W is even a tiny bit less than -1, the Big Rip is inevitable. It's just a question of when. Right? If it's -1.5, it happens about 20 billion years in the future. But if it's -1.01, it still happens. The Big Rip still happens, but it's just a little bit postponed. what happens in the Big Rip? 200 million years before the Big Rip, galaxies are separated. So the local group is disrupted. 60 million years before the Big Rip, the Milky Way itself starts to dissolve as dark energy overcomes the gravitational force. 3 months before the Big Rip, the Earth is ejected from the solar system as the force of dark energy overcomes the gravitational attraction of the Sun. 1 minute before the Big Rip, the Earth itself disintegrates as the force of dark energy overcomes the gravitational and electrostatic energy that attracts all of the atoms in the Earth, and the Earth itself is torn apart. And in the final moments, 10 to the minus 19 of a second before the Big Bang, dark energy is strong enough to rip atoms apart. And that's it. Atoms disintegrate, and the universe comes to a rather messy end. So it's weird, isn't it, the cosmological constant? We're right on the cusp of this very unstable behaviour. Fortunately, that's not what DESI tells us. DESI data implies this fate for the universe. It's weakening, dark energy is weakening, so the expansion of the universe eventually slows down and stops. The universe coasts to a gentle halt. And when we look at what that means in terms of the dark energy density, here it is with cosmic time. So that's 100 billion years after the Big Bang, a trillion years after the Big Bang. Dark energy becomes actually just kind of a minor episode in the history of the universe. It appears from nowhere, disappears to nowhere. It's almost just like a speed bump. So if I were to come, say, 100 billion years in the future and look for dark energy, I probably wouldn't find it. But it's still a bit peculiar because it was stronger in the past. That implies that the universe was in this phantom phase where in principle a Big Rip could have been possible if it had stayed there. So that's really weird. Why did the universe go into this phantom phase and how did it get out? It's quite odd. And when I think about what that means for the dark energy in my box, in the early universe it increased with time. So if I come a few billion, measure the energy density in this box after a billion years, another billion years, another billion years, I find the number is increasing. So it's a very, very strange thing to think about. You know, where did that energy come from? And indeed today, if it's decreasing, where is it going? So I'm pretty much at the end of my talk now. Maybe I've answered some questions about dark energy, but there are lots of questions that are still unanswered. We have, of course, theories that fit dark energy. One of the most popular ones is something called quintessence. Quintessence is a nice name that's kind of borrowed from the ancient Greeks, who had the idea of a fifth element. Quintessence is a fifth force of nature, so we have the electromagnetic force, strong nuclear force, weak nuclear force of gravity. Quintessence is this extra force. And it's quite a nice, appealing model because it's simple. Trouble is that the data doesn't fit this nice, simple, in some sense almost natural model. Because that natural model can't go into this phantom regime. This phantom regime is unphysical, and it's a natural model, so it must be physical, so it can't really explain the data. So we don't know the answer to that, and we don't really have a compelling model yet that really fits the data. People are working on it. I'm doing some work on it as well, but we don't have a good model yet that fits the data, so we don't know really yet what could be driving this strange behaviour. Why did dark energy wait 10 billion years? Remember I said in the early universe, no clue that dark energy is there. In principle, dark energy can have any value it likes, like a constant of nature can take any value it wants to. But the universe today is somewhat middle-aged, I'm sorry to say. It's been through its youth. Its youth occurred about 3 billion years after the Big Bang, when most stars in the universe were formed, and it's now somewhat middle-aged. So here we are in a middle-aged universe where dark energy is suddenly making its presence felt. In more or less the last 2 or 3 billion years of cosmic history, it could have made its presence felt at any time. Why wait? Why wait 10 billion years? the last point, which is a little bit technical, but there is a model of the very small called quantum field theory. And quantum field theory predicts that the vacuum is seething with energy. Little particles pop in and out of existence. It's called the vacuum energy. This seems like a very natural explanation for dark energy. And remarkably, we can measure it. We can measure it because all those little particles that pop in and out of existence, they interact with electrons and protons. So in a hydrogen atom, the electron swims through a bath of these virtual particles, and it affects the energy levels in the hydrogen atom. So we can measure its effect in the laboratory. We do so. It's called the Lamb effect. That's L-A-M-B. And the calculation exactly that we make in quantum field theory exactly agrees with our experimental results. And famously, quantum electrodynamics is accurate to 10 to the minus 14 decimal place, the most accurate physical theory. But the calculation that we get for dark energy from that quantum field theory, which agrees with the laboratory, is 10 to the power of 120 times bigger than the energy that we measure in the universe. No clue why. No clue why. But it does give the right answer from the laboratory. That's very, very weird. So yes, we're at the end of my talk here. I'm sorry to close on a bit of a downer of all the things that we don't know about dark energy. We do know a few things. Where are we going from here? We're collecting more data. DESI is still operational, despite Donald Trump. Fingers crossed on that one. So we hope to collect more data. We hope to refine our theory. Maybe in another couple of years' time, I might have some answers for some of those unanswered questions. And I'll close there, and thank you very much for listening.
Well, thank you very much. So, are there any questions? Yes, maybe.
Yes, Dr. Field. First off, great talk. Thank you so much. I want to know about Hubble tension and the S8 tension. Do these look better with a change in dark energy, or how do they? These are anomalies that we see.
Yeah.
Do they fit in with this?
It's a great question. Yes, and you're clearly well informed because you know about these problems and in other measurements that we make. Right, actually, more or less unrelated to these measurements. We do have a problem with the expansion rate of the universe. Just for the benefit of you, the Hubble tension is when we measure the expansion rate of the universe next to us, and we compare it to the expansion rate in a very early universe, which we can calculate from the cosmic microwave background. They don't agree. And they're very different. They should agree. It's the same universe. And the difference is 5 sigma, which is substantial, right? And it's a mystery. No one knows why this is. It doesn't appear to be connected, unfortunately, because when we take these evolving models of dark energy and we plug them in and we recalculate the Hubble constant, it actually makes the tension worse, unfortunately. So there doesn't appear to be any connection with the Hubble tension. The DESI results make it worse. So it's very unclear, the situation at the moment. Probably we need a better understanding of the theory of the models. The other perhaps explanation is maybe the data in the local universe is wrong. Could happen as well. The sigma rate tension, I would say now, is largely considered to be solved. And there was a recent paper out from a survey called KIDS, the Kilodegree Survey, KIDS Legacy. And this actually only came out a month and a half ago. But they've done a recalculation of their data, and they've done something very technical, which I don't fully understand. But when they did that really, really technical, complicated thing that you only need to understand if you're literally down in a basement for 3 years staring at the data and not seeing the light of day, the tension goes away. So it is widely believed that that was the result of a wrong calculation and it's not really a tension. So, yeah.
James?
I read a news article earlier this week that the timing for the collision of Andromeda with Milky Way is postponed a bit because of dwarf galaxies and hand-wavy stuff. Does this matter, or does it really irrelevant to your argument?
Actually, I haven't read the article. It's very interesting. Basically not really, because my argument, we don't really have data that's precise enough anyway. And I gave you a kind of glossed over account, right, which omitted some details. As you say, the Milky Way has satellites, Andromeda has satellites, that changed the calculation a little bit. To do this calculation properly, you probably want to simulate it in a computer with all of the other extra complicated stuff going on. And of course we would feed in this extra data, which is probably what that article is about, is that extra complication. So it can still be done. Right? You complexify the calculation a little bit, feed it into a computer, but it's basically the same thing, it's just a kept a little bit. But the key bit of missing data is obviously the masses that are there. We have some idea of the mass of the Milky Way because we have Gaia satellite data, which gives us the kinematics of all the stars whizzing around. From that kinematics, you can reconstruct the potential due to the mass, and so on and so forth. Andromeda, not so much at the moment. We don't quite know the mass of Andromeda. So, it will still work.
You probably roll your eyes when I ask this question because you've been asked a million times, but I do want to go back to one of the early questions about dark energy, whether there's another explanation that we're just not understanding something or not looking at it correctly. I mean, the analogy with the ether, for instance, everyone believed for a while it was there because they couldn't otherwise explain what was happening, but it turned out we misunderstood propagation of waves and so on. So is that now completely dead, or are there still people looking for maybe the flaw?
It's a very good question, and I'm absolutely not going to roll my eyes. And dark energy is profoundly weird. As I put in those unanswered questions, some of them are almost unbelievable. Right? So it's natural to be sceptical, right? That it's either a property of space or a property of matter. Perhaps it's something else completely different. And there are people who are seriously researching this. So there are a group of people that look at what's called modified gravity, and it's taking Einstein's field equations and complexifying them. In some sense, Einstein's field equations are like the simplest model you can write for gravity. It has certain properties, space-time metric, and certain symmetry properties. Now you can complexify things a little bit, and that's what the people who do these modified gravity theories do. They play this game of changing the law of gravity. If you change the law of gravity, in some sense, all bets are off. So they try to restrict their playground. Again, I won't go into the details of the way that they restrict the playground. So it's not so much the case that anything goes, but something reasonable goes. You can play this game and say that this dark energy doesn't exist at all, and it's just an artifact of modified gravity. I think there must be something. Right? There has to be something. It is either dark energy or it is modified gravity, because the data is now too strong to say it's just gravity and there's only matter. It's much more than 5 sigma. I forget the exact calculation, but maybe 6 or 7 sigma. But there is something that isn't matter in the universe, or gravity is different. But in principle, either one of those is a plausible explanation. I mean, of course, if it was modified gravity and not dark energy, would they take back the Nobel Prize from Adam Reason's? I'm not sure about that, but other possibilities are there. I didn't want to talk about modified gravity in this talk because it's, for me, I basically don't understand it very well. But the people who study it, the tool that they use to study it is gravitational waves, because where modified gravity makes itself felt is either on the very big scales or when you put a lot of stuff in one small space, and that's merging black holes. So there are people looking for signals of modified gravity from the signals at LIGO. It basically changes a little bit the signal of gravitational waves that we see on Earth. But yeah, it's a plausible avenue people are looking at. I don't know of any other alternatives, by the way, other than dark energy and modified gravity. Perhaps there are in the imagination of some theorists somewhere.
It is a worry, isn't it, that I mean, as you illustrated very well this evening, that dark energy is having to answer more questions. It's becoming more complex a subject. There are more phenomena that are having to be explained, which take us, it seems, further and further from the world we know. And I know quantum is a very good example of how that happened as well, and seems to be right. But all the same, the problem's getting harder rather than easier, isn't it?
Yeah. Yeah, it is, and I think we had a moment, it's a little bit kind of philosophical, but I think we had a moment of clarity perhaps in the first half of the 20th century where it was potentially believed that the end of physics was in sight. I think actually they believed that in Victorian times, perhaps as well, wasn't it? It was Kelvin who said something like that, perhaps, but he was wrong. But it was I think plausible to believe with the advent of quantum mechanics and general relativity, sometime around 1930, 1940, you could have believed that that was it, and that we would eventually reach a very simple, natural, and elegant view of nature. The universe is messy. I don't honestly know where this is all leading. I know it's exciting, right? Because for the first time in 30 years, we have a genuine paradigm shift. And I've heard George Staffy talk about this at the Royal Institution as well. So George Staffy is a very senior physicist from Cambridge who spent his life looking at this. And he said, he remembers obviously the time of 1998 and the Nobel Prize and all that. He said that was the last time we had a genuine shift in our understanding of the universe. And he said, like now, we have potentially another shift. By the way, he doesn't believe this in the slightest. He thinks the data is wrong, and he thinks that Einstein's cosmological constant is correct. Okay, that's his view. Entitled to it. But yeah, it's exciting times right now. So we like messy stuff. Perhaps it will all turn out to be simpler in a more elegant theory we don't know yet. But for now, it looks rather messy and complicated.
Two questions. First one is a really easy one. When you're working out the mass of Andromeda or our galaxy, do you have to take dark matter into account?
Absolutely, yes, because dark matter is still most of it.
Yes.
Actually, in our galaxy, dark matter is about 4 or 5 times the amount of normal matter. About 3 times. In the universe as a whole, it's about 5 times. Not all of that dark matter is in stuff is surrounding galaxies, but about 3 times as much dark matter as yes. So yes, you do, and that's a problem. That's why calculating mass is hard, because otherwise you just look at all of the stars and you go, well, they're all roughly between 1 and 2. Is laughing at me here.
Yeah, you have to do it.
Yeah. How else do you do it? Right? You count the stars and you say, well, they're all roughly about 1 to 2 solar masses. I've got 10 billion stars there. I've got this much mass, and that's the stellar mass of the Milky Way. But of course I don't know exactly how much dark matter is. I can work it out because it affects the speed of the stars. It adds to the potential. So that's how I work out how much dark matter there is in the Milky Way. I look at stellar speed, which I also get from Gaia data.
Don't you work out with Andromeda as well? Why is Andromeda higher?
Oh, sorry, I'll come to you in a minute.
That was an easy question. The second question may be a complete red herring here. But we talk about gravity and gravitational fields. Is there a field theory that would, bearing in mind Einstein's equation, energy can be transferred to matter, etc., that there is some sort of field within the void between in the whole universe that is what we are talking about here?
Yeah. I'll come to that question in just a minute because that's a slightly different tangent, but I will answer your question first. It's directly related to something. Sorry for the switcheroo there. We measure these things through very, very sensitive measurements from the Gaia satellite, and they're measuring the positions of stars at something like micro-arc-second resolution, which is like seeing a 5p piece on the moon. Very, very detailed measurement. We can only do that because the Milky Way is a lot closer than Andromeda. So in principle, something similar can be tried for Andromeda. You could do something called integral field spectroscopy, which measures the bulk rotational velocity of groups of stars, but not the details of individual stars. So you can tell something about the potential of Andromeda from that. But the data, as you probably guessed, I'm about to say, is not yet detailed enough to know precisely what that mass actually is. So yeah, there are some clues, roughly, but not precisely enough. As you remember from my graph, we need to know a bit about 10%. We're not quite there yet. I forget what the actual error bars are. Maybe it's like 50%, but that's kind of roughly where we are. It's not a billion miles away, so there's hope. And of course, there's new instruments being built all the time that will be able to do much more detailed observations. So there's hope.
So is that Doppler shift from one side of the galaxy?
It is exactly that, yeah. One side of Andromeda is coming faster towards us, one side going faster away from that. We can work out the rotation velocity. And if you do that as a distance from the centre of Andromeda, then you've got the map of the potential, essentially. That's how it's done. Yeah. To come back to
field.
to your question, back to the field.
Yeah.
That's the quintessence model, actually. Yeah. So if I say the word scalar field, does that mean anything to you?
I might have read about it, but it's over there somewhere.
The Higgs boson is something called a scalar field.
Yeah.
So we know scalar fields exist in nature. Scalar fields means they're kind of the simplest stuff that there is. In some sense, the Higgs boson is the simplest thing we can create as a particle. So it is widely believed in the early universe something called inflation happened, and it is again widely believed that is due to a scalar field, which we don't know what it was. We haven't detected it. But that did something a bit like dark energy and created an accelerated expansion of the early universe, which then ended. And again, that data seems to fit in with these simple models of a scalar field. So it's natural then to adapt that, to say that the same thing is happening again. And it's the same model, because it seems to work for the early universe, so why not borrow that model and say the same thing is happening again today? It doesn't fit the data. That's the problem. It is a natural and simple model and a plausible model. It doesn't fit the data. Whether it is or is not a field, I guess I couldn't really say. There are ways in which you can add extra fields, make them interact, do funny things, and you can still have a field generating the behaviour that we saw today. But the things that you need to do to get there look really weird to me. So possible, but weird.
I had a similar question about the connection between dark energy and inflation, because as you say, the data doesn't fit. In principle, it looks the same thing at a different scale, a different age, but it's a repulsive force. Inflation operates in a fraction of a second just after the Big Bang.
Yeah.
And without inflation, the universe cannot exist, apparently, or whatever. But is dark energy kind of another manifestation of more extended manifestation of inflation? But what you said is that the data doesn't fit for one and the other.
The high level difference between inflation and dark energy today, as in inflation, the universe had only dark energy in it and no matter at all, because the universe expanded so fast. All of the matter that predated, presumably there was some that predated inflation, but the universe expanded so fast. It's called E-fold, so it's e to the power of 60, which is a big number. So all of the matter that predated inflation was immediately gone, and the universe was filled with dark energy and nothing else. And then it is believed that at the end of inflation, all of that dark energy was converted to normal matter. But that's not the universe we see today, right, which is kind of almost 50-50. So that's the difference today. We thought originally it was like inflation, but the universe is 50-50, which is a very weird balance. That's connected with the why now question of why after 10 million
Well,
years.
this was before the origin of atomic particles, say. When atomic particles appear in 10 to the minus what? 30 or something, means that inflation is earlier. So inflation happens with pure energy. There is no matter at that time yet.
That's right.
Ah, okay, that's it.
That's
Thank you.
There might have been before, but it was just quickly diluted away. Because again, the expansion of the universe dilutes matter, makes it the same number of particles in a box. The box is now e to the power of 60 bigger. So there's virtually no matter left. It's all dark energy. But that's not what we see today.
It's fascinating, and it's fascinating to see the connection with Newton, as you do, and with Einstein and Eddington in that thing. We don't know what it is, but that was excellent. But what vision of these people
Yeah.
to. It reminds me of Democritus, because Democritus also talks about atoms, well, and void.
Yeah.
The void and the atoms occupy the space in the void, and playing with that idea of the nature of the universe. Fantastic.
And Einstein's arguments are subtle, so he's not arguing from the basis of any observational data. He's arguing from the basis of a principle, which is a and interesting. You know, it's a nice way to do physics.
Well, it's the
nature
other way around.
doesn't have to agree with our principles, but yeah, that was
Yes, but just to say, if the experiment doesn't agree with the theory, you have to repeat the experiment.
yes, there are people who believe that.
Change.
Well, I mean, the reflection of light by gravity, the solar eclipse and all that, it was a prediction. This 1.7 arc seconds, whatever it was. And Einstein said, go and observe the eclipse in 1919, I think it was. And they did, and it was right. That was what made Einstein a celebrity, because he predicted something which was completely bizarre.
Yeah, so Einstein owes his celebrity to Eddington.
Eddington did the observation, actually.
Yeah, that's
He
right.
went to the islands in somewhere
Somewhere in the South Pacific, wasn't it?
Gulf of Guinea,
Principe or something.
Principe Island, yeah. And there was another one in Brazil, because it was in Brazil and across the Atlantic. Fantastic. Yeah. These geniuses, I mean, really. Yeah.
This is a stupid question. I'm told, and you may confirm this, that part of it is data, basically the fact that it was all based on 3 points. And there's nobody's ever won a Nobel Prize for that little data. Is there any truth of that, or is this just scurrilous?
There's some truth in it.
Yeah.
Yeah, there's a little bit of a secret that's hidden in there. You remember the dots that I showed you? Okay, there were more than 3 dots, but you can calculate the significance of the data at that time in the method that I described and phrase it as a signal. Now, the dirty secret that's hidden is that they knew the universe was underdense, but that by itself, implying that matter only makes up 30%, doesn't mean that dark energy has to be the other 70%. The other 70% could be just nothing. Yeah, and it's called a curved universe, but it's technically an open universe. And it's allowed in Einstein's equations and perfectly possible, and in many senses a more obvious explanation than dark energy. Now, when they drew those dots, they didn't draw the data for a curved universe, for an open universe, but had no cosmological constant that was underdense in matter. If they had done that, they would have been unable to decide whether there was dark energy or just nothing. But that was buried somewhere in, it's somewhere in the paper that they say we assume that the universe is flat. Flat means that the densities have to add up to 1 in some form of units. So since the universe wasn't allowed to have nothing else other than matter, therefore it had to have dark energy because that was the only thing that was left. So it was a cheat, in other words, to summarise. And the reason why they believe the universe is flat is that's what inflation does. Inflation flattens out all of the little kinks and bumps in the early universe because it blows the universe up so big. Any of those initial wobbles are all flattened out. So inflation was widely believed to be true, but there was no observational data that told you it was true. So they had to assume the universe was flat to get their result. So yes, there's some
True,
truth.
but it's a bit
in
more
what
complex.
you're saying.
Okay, thank you.
Yeah.
Well, thank you very much again.
Thank you.